All right, guys, if you haven't read the context in the paragraph at the top of this handout, please do that first. Pause the video and do so now. Ultimately, in this question, let's imagine that a prosecutor has brought in a particular suspect and has applied a polygraph test to that suspect. What's the likelihood that they are lying given that the polygraph gives a positive test result? Well, we can use these data from these experiments to calculate that. So in this experiment, there were 51 subjects who were told to lie, 51 out of 98, and then the remaining subjects did not lie, and the objective was to determine how accurate the polygraph was. So in this experiment, the context of lying, the probability of lying, is 51 out of 98. That's about 52%, so we'll call that about 0.520. So the other information that we have in here, it was found that the likelihood of a positive lie detector test result, so a positive test result, given that we knew the subject was lying, so under the condition we knew they were lying, the lie detector gave a positive result around 82% of the time. So our probability can be 0.824. So the likelihood of a positive lie detector test result, there we go, given that we knew the subject was not lying because they were told not to lie, that was 0.319. Now notice, this is not the probability that ultimately we're interested in the real world. In the real world, we don't know if the subject is lying or not. The goal is to determine the likelihood that they are lying given that we've seen a positive test result. We've talked about order is very important when you calculate a conditional probability. So it's going to take us a little bit of work in order to calculate the probability that we actually want. So let's organize this here. We know that the probability of lying given a positive test result, we need both of them to happen. So in the numerator, we need the probability that someone is lying and we see a positive test result, and we have to divide by the probability of a positive test result. So the numerator we can find by using the general multiplication rule. We can find that by the probabilities that we already have. So here, the probability of lying and a positive test result. So we have to start with someone lying. Since this is an and probability, I can multiply. So I can multiply by the probability of a positive test result, given that I already know that they're lying. So I've got those probabilities already. So the probability of lying is 0.520. The conditional probability that I'm going to multiply by is 0.824. So I'm going to multiply those two together, and that will give me my and probability. So that probability, we'll do it to 3 decimal places. It's 0.428. So ultimately, that's the numerator that I care about. So what we need to do, ultimately, we need to find the probability of a positive test result. And in order to determine the positive test result, it's really going to help if we organize our probabilities by using what's called a tree. It allows us to organize a situation where there are multiple levels to the question. So the first thing that we have going on at the very beginning, when we think about this experiment here, the first thing that we did was we told subjects either to lie or not to lie. So that's the first level of this tree. So there are 2 decisions that happened at the very beginning. So either the subjects were lying or they were not lying. So we'll call that lying, and I'll call that not lying or lying complement. And I'm going to put those 2 probabilities into my tree. So the probability of lying was 0.520. So the only alternative is they're not lying. That's 1 minus 0.520. That's the complement. So that's 0.480. Now, look, these probabilities up here are conditional. Under the condition that I know someone is lying, this is the likelihood of a positive test result. So starting with a liar, so starting at this end of the branch of the tree, I can branch this off 2 more times. So given that someone is lying, we could see a positive test result, or we could see a negative test result. But this branch of the tree is a conditional probability. Given that I know they're lying, this is the likelihood of a positive test result. given that they're lying, here's the likelihood of a positive test result. That's 0.824. So if the likelihood of a positive test result is 0.824, I can do 1 minus the 0.824 to get the likelihood of, under the condition that someone is lying, what's the likelihood of a negative test result? That's 0.176. And now I can do the same thing under the condition that someone is not lying. So under the condition that someone is not lying, the likelihood of a positive test result is 0.319. So I'm going to branch my tree out again. Not lying, under that condition, a positive test has a likelihood of 0.139. So I can use that then to calculate the likelihood of a negative test result. 1 minus the 0.319, that gives me 0.681. So now I've organized the first level, whether or not the subject is lying or not, and the second level of this scenario, whether or not we get a positive test result. I've organized it into a tree. And because these are conditional probabilities, I can multiply along the tree. That's exactly what the general multiplication rule says. So look, under the condition that someone is lying, this branch of the tree, I can multiply by the probability of a positive test result given that they were lying in order to find the probability that they are lying and we have a positive test result. So this is what we did above. This is the probability of lying and a positive test result. We already did that up here, 0.520 times 0.824. That gives us this probability of 0.428. So I can find the other probabilities by branching along the tree. Lying, under the condition that someone is lying, what's the likelihood here then of a negative test result if they're lying? This is the conditional probability. So if I multiply these two probabilities together along the tree, I get this probability. The probability that someone is lying and we get a negative test result. That's the 0.520 times the 0.176. That gives me, I'll call it 0.092. So here's my next probability. Under the condition that someone is not lying, what's the likelihood of a positive test result? Right here. So if I multiply these two together, I can get the probability that someone is not lying. So lying complement and a positive test result by multiplying along those two branches of my tree. So times 0.480 multiplied by 0.319. That gives me, we'll call it 0.153. And then here, lying, here's the probability given that they are rather not lying, 0.480. This is the probability given that they're not lying that we get a negative test result. So multiplying along this branch of the tree, again, I can get the and probability. Lying, the complement of that, the complement of lying, they're not lying, and a negative test result by multiplying along those two branches of the tree. That gives me the 0.480 times 0.681. That's, we'll approximate it at 0.327. And now I've got everything that I need because ultimately I already know the numerator. The probability that I care about here is the probability of lying given a positive test result. So that's what we were looking at up here. And I already know the probability of lying and a positive test result. That's my numerator. That's the 0.428. That's this very first set of branches in the tree. So I've already got that. The whole point, though, of doing the tree was in order to calculate the likelihood of a positive test result. A positive test result can happen two ways. We can be lying and see a positive test result. The alternative is that we could be not lying and see a positive test result. Those are the only two ways that we can get a positive test result, and I can add those two probabilities. Again, this is the probability of lying and a positive test result, or the probability of not lying and a positive test result. Or means add, and these are disjoint, or these are mutually exclusive events. They can't happen at the same time. You can't be lying and not lying at the same time. So it's perfectly acceptable to add these two probabilities together. I don't have to worry about if there's any overlap or if there's any double counting here because they can't happen at the same time. So the probability of a positive test result is the 0.428 plus the 0.153, that gives me 0.581. And now I've got everything that I need. So what we really care about ultimately is the probability of lying given a positive test result. So lying and a positive test result, my numerator I already had at 0.428. The denominator is the likelihood of a positive test result. That's the 0.581. So the ratio of those, 0.428 divided by 0.581, if I calculate that, that gives me 0.737. And ultimately, that was the whole goal of organizing and calculating the probabilities this way. So understand the order is very important. I already knew from the experimental data the probability of a positive test result, given that someone was lying. That happened about 82.4% of the time. But that's not what prosecutors or detectives or the police face when they bring in a suspect and apply a polygraph to them. They're asking a very different question. What's the likelihood that someone's lying if we see a positive test result under that condition? Well, that probability is 0.737.